Okay, let's shift and go to a completely different topic. I'll try to give you an introduction in magnetism. So let's start with the very simple concept. There are two types of magnetic systems, and the main point is, are the magnetic moments localized? Are they coming from delocalized systems? There is also a borderline case for some F-electron system where it's not clear whether the magnetic moment is localized but coming from itinerant electrons. So let's take some very simple examples to get the definition. What is a ferromagnet? If you have a ferromagnetic system, for example, PCC ion, you have a magnetic moment at each atom, and the magnetic moment have the same orientation at all the atomic sites. Then you would call this ferromagnet. You have a finite magnetic moment, magnetization. If you have an antiferromagnet, then you have a magnetic moment which is in one direction and the other one in the opposite direction, so the whole total magnetization is zero. So they have the same amount of spin of magnetic moment in one or the other direction. So this would be a typical antiferromagnet, and chromium is one example, and I'll show that a bit later. There is a mixture of the second antiferromagnet, ferrimagnetic cases. If you have a magnetic moment up and down, but the down moment is different from the up moment, then you get a finite magnetization, and this is called, such a situation is called ferrimagnet. There is a more complicated system, which is non-collinear magnetism. I'll show you one example, and it will be discussed later on. But here I restrict myself to the collinear cases. Collinear means it's parallel or anti-parallel, no angle between the magnetic moments. So non-collinear means that the magnetic moment at a different atomic size vary with angle. Then it's non-collinear. So this is the basic nomenclature, what we have. Now let's take the simple example, iron, cobalt, nickel, for example. The crucial quantity is the Curie temperature, and the magnetism disappears above the Curie temperature, and below it's magnetic. So you have magnetism below the Curie temperature and no magnetic moment above the Curie temperature. So where does it come from? So the Stoner theory for itinerant electron magnetism is that the carriers of magnetism are the unsaturated spin of the d band. So take iron, and I'll explain that in a minute, is you have an exchange, and this can be treated with a molecular field. Must confirm Fermi statistics. But let me illustrate the Stoner theory in a very simple picture. So if in a non-magnetic case, the number of spin up electron and spin down electrons is equal. So you have the same number of spin up and so the same you would have in any molecule. If each orbital is occupied spin up and spin down, it's non-magnetic. Now let's assume that you have schematically a density of states like sketched here. There is the phenomenon of exchange splitting. So if you shift the spin up and spin down energies in energy by a certain amount, delta E, indicated here, then if you have this situation, then you have more electrons of spin up and less with spin down, majority spin, minority spin. And the difference between the number of spin up and spin down electron gives you the magnetic moment. So this is the key element. Then you have the magnetization, the difference, a different occupation between spin up and spin down electrons. There can also be orbital moments, and now the crucial quantity is the Stoner criterion, which you can derive, and I'm not going to describe that here, but basically it depends on the density of states at the Fermi energy in the non-magnetic system. So let's sketch it here. The Stoner criterion basically means the Stoner parameter I times the density of states at the Fermi energy. What Peter just showed in with phonons, you have the same thing in magnetism, is the curvature at the non-magnetic case the energy going up or going down. If it's going down, there must be magnetic solution. If it's going on, it stays non-magnetic. And the criterion is the Stoner criterion. If the density of state is high at the Fermi energy, the Stoner criterion is satisfied. Now let's look at iron. Now this is a calculation of a non-spin polarized ion. Then you see this solid line, and the density of states at the Fermi energy is high. This is 1 divided by the Stoner criterion, and so you see for iron, the Stoner criterion is satisfied. If you look at the same thing for FCC iron, then you see the dashed line here. The FCC ion, the Stoner criterion is not satisfied. That for FCC ion is non-magnetic. So the Stoner criterion from a non-magnetic calculation allows you to predict whether a system wants to be magnetic or non-magnetic. There are exceptions to this, so this is a rule. So there can also be cases that there is a lower, it is going up the energy, but later on you have a situation, something like this. So this is an important problem. Let me try to illustrate this for iron. So if you have a density of states for iron, then the spin up and spin down density of state look identical. And here is the Fermi energy, and the Fermi energy falls in a range where the density of states is very high. Stoner criterion is satisfied. Now what happens basically in this system is you have a high density of states, and you have an exchange splitting. So you shift the bands of this one spin direction up and the other down by a certain amount. Then you simply shift the density of states. That was the old Fermi energy. But now we have a new Fermi energy, and we should have this common Fermi energy between the system. And then you occupy more of the spin up and less for the spin down state, and that causes magnetism. Yeah, so that's the very simple picture of a magnetic structure. I remind you on this graph that it could be crucial whether you have a magnetic solution, yes or no, depending on the functional. So LDA would give you the wrong result, and GGA will give you the right result in this particular case. So the functional can be important. Now let's look at the iron and alloy. Let me show you here that the dotted line here is the non-magnetic case. And if you now do a spin polarized calculation, then you find that the iron, the solid line, spin up is moved down in energy, and the spin down density of states is moved up in energy. So it is this is a real calculation, not the sketch which I did before. And then you see this simple picture works to a good extent. Now, if you take cobalt, HCP cobalt, then this is called a weak ferromagnet because the Fermi energy, the D bands, this high density of states, is not fully occupied, while in HCP iron, for the majority spin state, they are fully occupied, and such a case is called strong ferromagnet. So you have a weak ferromagnet, a strong ferromagnet. Now let's see whether we can understand the density of states. Volker came up with a very simple picture to show where does it come from. Now if you have an iron, then you have nearest neighbor distances, and the nearest neighbors forms bonding and anti-bonding states, and this is the basic for these two peaks. This is the bonding and the anti-bonding of the nearest neighbor interaction. But then you have next nearest neighbor interaction, which are weaker, and you also form bonding and anti-bonding states. So you, in this very simple picture, you can guess, so to speak, how the density of state looks. This is the bonding, anti-bonding, and this is the from the next nearest neighbor picture. That you get a simple picture, which is nice always that you can explain that. And that is what you really get. Now let's try to do the same concept for iron cobalt. And the reason for showing you that, you have to be careful. If you show a very simple picture for one case, it doesn't work in the next case. So you have to be careful. And I'll explain the concept of Wigner delay time. So let's start out with iron, and then look at cobalt. And if you now take an alloy, But take iron, then one peak, double peak, the other peak, and at the shoulder you have the Fermi energy. Cobalt has one more electron, therefore the Fermi energy moves up, but the two density of states look very similar, the two. Now, if you take an alloy, and to simulate an alloy, you use ordered structure. So you use, for example, the Häusler alloy, cobalt 3, iron 3 cobalt, or iron cobalt 3. Häusler alloys, then you have an ordered structure, and then you could say it's 25% or 75% of this alloy. As a crude simulation, it's ordered, so the real alloy would be different. If you took to the 50%, then you could use a cesium chloride structure. At the edge atom you have iron, and in the center cobalt. But you can also use a single phase, for example. Then you say this center iron is surrounded by 4 iron and by 4 cobalt. So it has a different coordination in the nearest neighbor. But these are details that is not so crucial from what I want to explain. Let's look at such a case. Is it itinerant? Is it localized? And for that purpose, we can use the difference between the spin up and spin down density. And then you see, and the integral of this magnetization density gives you the magnetic moment. And what this figure shows, maybe I sketch it here. This is the cesium chloride structure. So you have the iron in the corner and the cobalt in the center. And I plot this plane here and show the magnetization density, which is the electron density for spin-up electrons minus the electron density for spin-down electrons. And the integral of this quantity gives you the magnetic moment. Now what you see if you plot this quantity, it is 0 here, the dashed line. Therefore, you see it's highly localized, and if you integrate it, this would be the moment of the cobalt atom, and this one would be the moment of the iron. So the magnetic moment, you could say, is localized, although it's coming from an itinerant picture. This is an old paper. What I like to show you here, and I make this very brief, we can go to Wigner delay times, that you come to a very simple atomic picture. So let's put it this way. If you have a Maffei-Dinh potential, then one can derive a scattering quantity, which is the phase shift, and you can write this, and I skip the details here, how to derive it. So basically, the idea of the scattering mechanism is, maybe I briefly go here, you have to add to the potential this L plus L plus 1 divided by R squared, this quantity, and this is plotted here. So in the sense of scattering, you can find so-called resonance states. And if you plot this function, the potential, plus the L plus L plus 1 divided by R squared, you could say if you have a scattering coming in with a certain energy, let's take this picture here. If you come with a low energy, then the scattering doesn't enter the potential because the barrier is too high. But if it comes here, it enters and it stays here for a finite time. That's the Wigner delay time before it scatters off again. If you increase the energy, it comes in and goes out very fast. So there is a resonance maximum of resonance. And this allows you, that is plotted here, that's the phase shift, and the derivative is the Wigner delay time. And the reason for using that is that you can now derive with this quantity, let's say, an orbital picture, and then you have a very simple interpretation. Let's take the series iron, cobalt, nickel. What's going on? Iron, cobalt, nickel, the atomic number increases and the corresponding D levels are decreased. Now then, for each of these states, we have an exchange splitting, the spin up and spin down states. And so let's take just iron, cobalt. If you take the spin up electrons, the energy of spin up electrons for iron and cobalt are identical, more or less, which you see here in the phase shift. But for the spin down electrons, they're different. This is this picture here. And so you have to be that you need to take that into account. So basically, if you plot the density of states now for iron cobalt, the 50-50 compound, then you see for the spin up electron, it looks identical for iron and cobalt because they have the same energy, the same scattering, no difference. But for the spin down, it is different. And this is the chemistry, so to speak, covalent bonding sometimes, covalent magnetism it's called. So you have here more cobalt state and less iron, and here more iron states and less cobalt state. And that can be easily understood. If you look at the spin down orbital energies, they are different. Spin up are the same, but spin down are different. And now you can use the simple picture again, bonding, antibonding state. So the bonding state have more cobalt character, and the antibonding state have more iron character, as you know from a simple MO diagram, bonding, antibonding state. So a rigid shift, what would you obtain if you would just shift the density of states like I did in iron? Now then you would have the same density of states for iron and cobalt in both spin direction, but what would that mean? That would mean that you have to move half an electron from cobalt to iron. You make it ionic, so to speak, and nature doesn't want to do that. Iron and cobalt have no difference in electronegativity. Therefore, you have a different scheme, and the different schemes means this covalent magnetism, and then you have more cobalt states than iron state, and the number of cobalt electrons remains the same. The reason for showing that is you have to be careful with a simple picture which works for iron, that you should not extend it to compounds. So you have also to use, so to speak, the difference in the chemical situation. That can also be done with this schematic diagram as I showed you before. Peter was mentioning chromium. Now let's take chromium. Chromium has a cesium chloride structure, so to speak. One chromium has spin up electron, but the chromium in the center is different, has spin down. And if you do a calculation for a chromium, you can use symmetry, which tells you that the two atoms have equivalent, are related by symmetry. So basically, schematically showing the chromium 1 has a spin up and spin down density of states, and the chromium 2 also has a spin up and spin down density of states. But by symmetry, you know what is spin up here is spin down here, and what is spin down here is spin up here. So you only have to do one calculation, and the other quantity you can compute automatically by using symmetry relations. And that is done, that saves computer time, basically. And you only do one spin calculation, and the rest is not needed. Let's show another example. I'll show you one strange situation which we studied some years ago, the sodalite, zeolite. It's basically a cage, and if you have a tetrahedra which is linked and the oxygen, and if you have alternating aluminum and silicon, it forms this cage, and this is called a sodalite. Now, since aluminum has 3 valence electrons, silicon has 4 in the cage, you are missing 3 charges. Therefore, this is not stable. And how to stabilize it? Per cage, you're missing 3 charges. How do you get 3 charges? You put it in sodium. But by symmetry, there are 4 positions. So you put in 4 sodium atoms, shown in yellow. And so you have 1 too many. And the 1 too many means you are left with 1 electron, and the 1 electron forms a color center in the center of this cage of sodium atoms. And the strange thing is this, there is no atom, this is just a trapped electron, and this trapped electron forms an antiferromagnetic structure with the trapped electron in the next cage. So this is a funny extreme situation, and if you look at the spin density of this system, then you see that you have spin up at this point and spin down at this point. It's a trapped electron. So you even can have magnetic situation like this. That was done many years ago, but it's an interesting case. Let me show you a few examples where you could have interesting behavior in magnetism. And we have many years investigated Invar alloys. What is an Invar alloy? If you take the iron nickel, this is known to have no thermal expansion. So it's one of the materials, if you heat it up, there is no thermal expansion. Every material, if you heat it up, expands. This one doesn't. The history was an interesting measurement on the Eiffel Tower. So the history goes back 1897. And what they have done, they've used an iron nickel wire on the Eiffel Tower, and the wire doesn't expand, so it doesn't change length, but the Eiffel Tower does. So what they found is that the recording here, that the Eiffel Tower expands and contracts according to temperature. That's temperature, that's the expansion of the Eiffel Tower. So they found there is a thermal expansion of the Eiffel Tower, but not of the alloy. So this is Invar behavior. Now the question is, can you understand such a behavior? So this is the thermal expansion coefficient for this alloy, 65% iron and nickel, and you see around room temperature this thermal expansion is practically zero. So this is very unusual and has many applications. In the old days, the television screens were built with the Invar alloy. If you heat it with a beam, it heats up, and you don't want that. You have a thermal expansion. But it was used for many applications. Now, how can you understand it? And so the old story about this was from Dick Weiss. He said you have two states. You have one ferromagnetic, high moment, large volume, and if you thermally excite it, then you go to a different system which has a small volume and a small moment. So you change the magnet, so it's an effect of magnetism that you can explain what's going on in this situation. Let me not go to the details. But the reason for showing you that is now you can try to understand, if you use this iron nickel alloy, then you can use the same what I did for iron cobalt, that you use a pure nickel FCC structure, and that would be a pure iron in the FCC structure, not in the BCC structure. Now, the Invar alloy is close to the copper 3 gold for this case, and what I show here, and that is the new feature which makes it interesting, you can plot the volume here, and here you plot the magnetic moment. So you get the energy surface of volume if you expand the lattice, but also the magnetic moment. And if it's ferromagnetic, like in this case, then you get a clear minimum. And if it's non-magnetic, there is only a volume minimization, but no magnetic moment. And the Invar alloy is one where you have a very flat surface. And this very flat surface also causes computational problems. So what we have done in this situation for the Invar alloy, if you start at 0 Kelvin in this minimum and you allow magnetic fluctuation, then you can estimate how the system would evolve at final temperature. And if you see, you slowly follow this curve here at 100, 200, 300, and at the Kelvin, at the Curie temperature, the magnetism disappears. So you need this surface. So how can you compute the surface, which means the energy as a function of volume and magnetic moment? And this brings me to this concept which is implemented in the WIEN2k, which is the fixed spin moment method. And that is something one should briefly understand. So how can we analyze such a system? Take FCC cobalt. If you apply a magnetic moment, then you can, by applying a magnetic moment, you increase, you get a magnetic moment. By applying a field, then it jumps to a high moment. And if you have a hysteresis, if you switch off the magnetic field, it comes back. So you have such a situation. Now let's do it from a mathematical point of view. If you are in this range, then you have three solutions. One here, and one here. Which means you have three situations which have the same energy. Which in practice means the calculation doesn't converge. So if you have a situation, in this case, the magnetic moment, the energy as a function of magnetic moment is a very flat surface, and it's extremely difficult. It never converges. And we had extreme difficulties running that. And then we came up with a new idea and said, let's fix the moment. So let's do a calculation. The conventional one, the Fermi energy of spin up and spin down is the same. The number of spin up and spin down is given. And if you do a calculation, you get as output the magnetic moment. Now let's turn it around. Let's use the magnetic moment as an input. I want a situation where I have one Bohr magneton as a magnetic moment. Okay, I still have the same number of spin up and spin down electron, but then I have to release the Fermi energy equilibrium. And if I do that, I can do a fixed spin moment calculation. What that means, I say I want a solution with one Bohr magneton, fix it, and then I get a very fast convergence and get 1 point. So I have to do many points to find the minimum. But that is the basis for deriving this energy surface, which I showed you before. And this is implemented. Now you can also show it in a different diagram. What you do, usually you apply a field, and then you get a moment, and you have this situation. Now, mathematically speaking, what you do, you interchange the dependent and independent variables. So you say, I fix the moment, and now I compute the field afterwards. So you interchange the two things, which is unphysical, but from a computational point of view, the easy way. I fix the moment and compute afterwards which field would be required to obtain this moment. And so that can be done, and that has been done in these papers. Okay, let me quickly show you one more example, the chromium dioxide, because I think there is also somebody here that was Peter Greenberg, the Nobel laureate, with the giant magnetoresistance, Albert Pferd. They received the Nobel Prize for the magnetoresistance. And in this Nobel Prize committee, they also quoted one of my papers on chromium dioxide. And I like to show you this background to show you there is a strange situation what can happen in chromium dioxide. That is the case. If you have chromium dioxide, you have a spin up situation where you have a metal, and for the spin down, you have a gap. So you have an insulator for one spin and a metal for the other system, and this is called half metal. Why is this interesting? Nowadays, if you want to do spintronics, then if you have your Fermi energy, at the Fermi energy you have only one spin occupied. The other is a gap, and therefore there are no states with the other spin. Therefore, if you want to have spin injection in the material, these are the materials which people like to have, and they have studied many Heisler alloys which show this property. There is also one poster on one of these Heisler alloys which shows this property. So basically what happens here is if you take chromium dioxide, that the spin down density of states looks very similar to the rutile TiO2. So chromium, one spin looks like titanium, and the other spin looks like ruthenium dioxide, which is metallic. So you have a metallic situation and an insulator in one material, and that's half metallic, and that makes this material interesting. So you shift from this one in this and this in the two spin directions, and that makes it interesting. I think Robert will talk about the non-collinear magnets, but I show you one picture just to illustrate what that means. If you have magnetic moments in such a crystal structure, If they orientate non-collinearly, then you have to use a different description. That is ruthenium dioxide. Let me skip that, and I thank you for your attention.